Okay, this is a good question. I like this one a lot. Make sure you've paused and read the video. We got ourselves an ellipse here. We're going to squeeze, inscribe a rectangle inside the ellipse, and we want that rectangle as the maximum possible area. So let's draw this out. You should recall from pre-calculus that this ellipse is going to have a long axis that's 2 by 2, 2 on either side of the center, and a short axis that goes from -1 to 1. There's 2, there's -2. We're going to get some ellipse that kind of looks like this. Okay, now inside that, I'm going to try to put a rectangle. So let me change the color here. Let's go red. Okay, so let's say we've got some rectangle. We'll just draw some random rectangle in here. That rectangle, I've gone out some distance x. So I'm calling x this distance here. And I'm calling this distance vertically here y. So the entire rectangle is 2x long and 2y high. That's important, and that's easy to mess up, to realize that if this is x, the entire thing is 2x. Okay, so area of the rectangle is length times width, 2x times 2y. I need every single time, write down the thing you're trying to maximize or minimize and figure out how to write it using only one single variable. So I need this in terms of just either x or y. I'm going to write this in terms of x. So I know that whatever this point is in terms of x, I know that y value right there. That y value right there is the square root of 1 minus x squared over 4. How did I get that? By moving this to the other side, taking the square root of both sides. Why didn't I use the plus or minus? If I wanted the minus, that would have been this spot down here, and I just want the absolute value. I just want to know that positive y value so that I can get this double y. So if I go over x, I'll be going up square root of 1 minus x squared over 4 to hit that point right there. Now I have y in terms of x. I could say a as a function of x will be 2x times 2 square root of 1 minus x squared over 4, which I could rewrite as 4x square root of 1 minus x squared over 4. Now I have written the thing I'm trying to optimize in terms of only one letter, one independent variable. And then from here, it's always the same. We're going to take a derivative, set it equal to 0. We're going to check our endpoints and see who's the biggest and who's the smallest. Let's write our domain. What x values make sense here? What's the smallest length I could have mathematically would be 0. And what's the biggest that x could be? 2. And it should be pretty obvious to us that when x equals 0, my rectangle has 0 area. And when x equals 2, that would be 4 over 4, 1 minus 1 is 0, you get 0. So both of the extremes would just be a line or a line segment. We would have no rectangle. So we know from the extreme value theorem, we know that this function is continuous. It's differentiable on the interval from 0 to 2. It's going to reach a maximum and a minimum someplace in that interval. Might be the endpoints, might be someplace in between. I know it's not always equal to 0. I know not all rectangles are 0. So that can't possibly be the maximum. The maximum has to occur someplace between 0 and 2. And those maxima will occur at critical points. So I got to find either places where the derivative doesn't exist or equal 0. Okay, so let's take the derivative. I have to use product rule here. So I'm going to call this my first function and my second. Derivative of the first. Derivative of 4x is just 4. Leave the second alone. Plus, leave the first alone. Now I got to take the derivative of this guy. So we want to think square root of 1 minus x squared over 4. Think of that as 1 minus x squared over 4 to the 1/2 power. So the 1/2 will come down. Leave the inside alone. And drop that power down by 1. So that'll become a negative 1/2 times the derivative of what's inside. This is chain rule. Derivative of 1 is just 0. Derivative of negative x squared over 4 would be negative 2/4 x. Okay, so now let's clean this up. A prime x. Can't really do anything with this. So I've got that 2 and that 2 that will cancel. I've got that 4 and that 4 that will cancel. I've got this negative. I've got an x and another x. I'm going to get negative x squared times this. And I'm going to write that as that radical down in the bottom. Okay. So you may want to go through and check all the details here. Make sure you see where I got all that from. Okay, I want to set this equal to 0. So I would, like there are a bunch of ways we could, but I shouldn't say there are a bunch of ways. There's really not much you can do to solve this algebraically other than moving this to the other side. Okay, now cross multiply. I'm gonna need some extra space here. I'm gonna make all this a little smaller. Okay, so cross multiply here, or another way to think of it, multiply this up. Now think about this. Make it big so you can see. I've got square root of junk, and when I multiply this up, I'm multiplying it by itself. I'm multiplying square root of stuff times square root of stuff. Like think of if I had square root of 7 times square root of 7, that would be square root of 40. That's just 7. That's what it means to be a square root. When you multiply it by itself, you just get stuff. So this times that, when I multiply that up, I'm just going to get what's inside. And then on the other side, we just have an x squared. Now I would distribute here and get 4 minus x squared equals x squared. Move the x squared over. 4 will be 2x squared. Divide by 2. Take square root of both sides. We don't have to worry about the negative one because we've already said our domain is 0 to 2. We get x equals square root of 2. Then the maximum area. So the max occurs when x equals root 2. And the max area, the actual value, is a of 2, not plugging in here, I'm plugging into the original, plugging in a 2 here, and you can go through all the math and check it yourself. A of root 2 is 4. Okay, it's a good place to stop on that one.